It's finally here! 2 weeks later, we're finally bringing you another episode of Tensor Calculus for Physics, or whatever I decided to call this series. Today we're going to be talking about two index tensors. More specifically, we're going to talk about two specific two-index tensors that are frequently encountered throughout undergrad. You see, we're not ready yet to start tackling physics problems by saying, I'm searching for a mathematical object that transforms this way. No, what we're going to be doing is we're going to be looking at cases that we already know how to solve, that are special cases, and relaxing the constraints a little bit and making it more general. And when we do that, we're going to happen upon these mathematical objects that we're going to call tensors. In the next video, I suspect that we'll start talking about how these things transform. So today we're going to be talking about the electric susceptibility tensor and the inertia tensor, and we're going to start with their analogous, more simplified version of themselves and see how it generalizes to these mathematical objects. So let's get started. So we're going to kick things off with the electric susceptibility tensor, and I want to paint a little picture in your head first. So imagine we just have two parallel plate capacitors, and what we do is we're going to insert some kind of dielectric material. We're going to have some like plastic or something that we're putting in between the parallel plate capacitor, and then we're going to charge it up. And what's going to happen is the molecules inside the dielectric are going to expand and move around a little bit, and in doing so it's going to create a bunch of different new dipole moments within the dielectric. Now we can describe the polarization of this dielectric material now, where we have some vector p that describes the density of these dipole moments. And typically this vector p is going to be pointing in the direction of the electric field that it's subject to. So we have our little permittivity of free space, some Greek letter chi that we're about to get into, and then the electric field. Now, the one way to think about this is if we have n particles within some unit volume of this dielectric, what we're effectively saying is that P is equal to n times the average P. So this is like if we're taking a macroscopic look at this. And in this equation here, what this is saying is that P is the spatially average dipole moment. And in this top equation here, this Greek letter chi is what's known as the electric susceptibility of the material. And it's unique to the dielectric that is being used. But in this form, what this is telling you is that if we know that E is pointing north, then P is pointing north. But that's not the case for all dielectric materials. So there are certain cases where if E is pointing north, then P could be pointing in any direction. And we need a way of describing that kind of material. And this is where I'm glad we took time in the last video to learn how to express vectors as matrices. Because in reality, the way that we can write this whole equation is by saying we have sum px, py, pz, some column matrix is equal to epsilon naught times some 3x3 matrix, chi xx. Now, in the case to where everything is pointing in the same direction, P is pointing in the direction of E, what this tells us is that this chi can be expressed as a 3x3 diagonal matrix. Okay? A 3x3 diagonal matrix with 0 off-diagonal components. In other words, we have xx, we have 0, 0, 0, chi yy, 0, 0, 0, chi zz, times our column vector that is the electric field. So we have ex, ey, ez. And if we write this out, we expand this out, what this tells us is that if everything's pointing in the same direction, this tells us that we have px is equal to epsilon naught chi xx, xx, ex. We have py equals, oops, this is yy, ey, and so on for pz. Now what I'm saying is that I want a way to generalize this to if P depends on more than just, or say the ith component of P depends on more than just the ith component of the electric field. Well, what that means is that we're going to have to introduce some off-diagonal components to this matrix. Okay? So if instead of having these off-diagonals being zeros, we let them be their corresponding x, y, and all that good stuff, so let's explicitly write this out. By the way, if you have the book that I've been using for this little series, the book does not put it this way. It just sort of goes straight into generalizing it into the polarizability, or sorry, the susceptibility tensor. But I really prefer expressing this in terms of matrices. If you guys prefer that I sort of skip steps and get straight to the point, that way these videos become a little bit shorter, let me know in the comments section. But it wasn't explicitly clear to me at first to express it this way, which means I figured it might not be all that clear to those of you who are watching, which is why I try to take the time to go through these steps. But anyways, if we're letting pi depend on more than just ei, that means we need some off-diagonal terms, which means that we're going to be writing chi equal to some 3x3 matrix. So we've got chi xx, chi xy, chi xz, chi yy, nope, that's yx. Okay, so this is now something that we are calling the electric susceptibility tensor. Now, we've expressed it as a 3x3 matrix, but that does not mean that all 3x3 matrices are tensors, because as we showed in the first video, or not as we showed, as I told you, tensors are defined by how they transform. But we needed to construct this mathematical object in order for this to depend on more than just that. Okay, so if we're letting chi be expressed this way, then that tells us that if we want to look at, say, the y component of the polarizability, so py, okay, the epsilon naught doesn't change, that's epsilon naught, and now it's chi times e. Okay, so we're going to be looking at, let's see here, that's going to be chi yx. It's going to be x, actually. So what we've done here is we've generalized this to the case to where the ith component of p doesn't just depend on the ith component of e. I know I've said that a million times, but I think that's important, and I hope that's clear here by now, since we've expressed it in terms of matrices. And you can go through the motions of doing this for the x component and the z component. They're defined almost exactly the same, right? Because all we're doing is the first index here matches with the component, and then these are the terms that are being summed over, the second index and the electric field. So that we can shorthand this a little bit by saying the ith component of the polarizability vector is equal to epsilon naught times the sum, that's sum over j, of chi, so that's going to be I, j, e, j. So here we've defined the component of the polarizability in terms of the component of the electric susceptibility tensor. Now, one quick thing before we move on is if this part here was just a little bit unclear, keep in mind that all I did was I took the y row to give me, and then multiplied that by, the ex, ey, ez. So that's where this comes from. The next tensor that we're going to talk about is the inertia tensor, which is actually probably the first tensor that you encounter in undergraduate physics. So what I like about choosing these three tensors specifically is that they're generalizations from their special case counterparts. So if we think about the analogous moment of inertia, we can think about some kind of rigid body rotating about a fixed axis. And we can split that, say we have like a sphere or something like that, and we have some infinitesimally small chunk of mass that we're calling dm, and we can say that we have some distance from this axis that we are rotating about, that's some distance s, and we can define the velocity that this little chunk is rotating about, rotating around its circle as, say, v is equal to s times its angular velocity. we can start to calculate things like the moment of inertia, which is really just a measure of like how much torque you have to apply in order to reach some kind of angular acceleration, by remembering that the total angular momentum is just going to be the sum of all of the angular momenta. So since we're dealing with infinitesimals, this sum becomes an integral. We have our r cross v dm, because we're adding up all of the little masses, all the little mass chunks, which in our case, this simplifies to just saying that this is going to be our omega vector times s squared dm. And we could do things like calculate the moment of inertia for some mass m, a distance r, away from the axis of rotation about some uniformly distributed mass or distribution of a sphere with, say, density equal to 1. That's pretty trivial. I'll let you guys do that. Just kidding. Let's go through it real quick. Okay, so let's go ahead and do that. So I'm saying we have some mass m, radius r from the axis of rotation, and we want to calculate the moment of inertia. Well, what is the moment of inertia? A moment of inertia is just going to be this thing right here. This is the definition. So I is defined to be the integral of s squared dm. Okay? So if we want to find this for a the mass uniformly distributed sphere of density 1, well, let's just go ahead and calculate this. Well, if it's some angle from the z-axis, say, then we can say that s is just going to be let's make that a little r, is equal to r sine theta, right? And we can substitute this in. We're in spherical coordinates, so this becomes the integral of r sine theta squared, and then the dm is just going to be this measure here, the r squared sine theta dr d theta d phi. So this is a triple integral. I only wrote one integral sign, but that's a triple integral. Okay? And let's go ahead and evaluate this. Where's the rest spot? Let's go over here, I suppose. Can you see this? Yes, you can. Okay, so this integral just simplifies to, we got an integral from 0 to 2 pi d phi, integral from 0 to pi of sine cubed of theta, integral 0 to big R, because that's our radius, of r to the 4th, dr. So this gives us a factor of 2 pi. This gives us a factor of 4/3. This gives us a factor of r to the 5th over 5. And then we can just use sort of the definition of density to make a little bit of a simplification here, because remember that the density is just the mass over the volume, which means that the mass is just equal to the volume times the density. But the density is going to be 1. Let's make that just a little row. The density is just 1, so that's not important to include in this. So that tells us that we have a mass that goes as 4/3 pi r cubed. We can solve for r cubed, so r cubed is equal to 3/4 m over pi. And substitute this into, I'm sorry, I'm writing all over the place, but I'm kind of I wrote a little bit too big, into this r here. Okay, and then we get that this is just going to equal, well, the 4/3 is going to cancel with the 3/4, right? The pi is going to cancel with the pi. So this tells us that I is going to equal 2/5 m r squared. So here we've calculated the moment of inertia for some part, a distance r away from some fixed axis that I'm choosing to be the z-axis. And yeah, it's pretty straightforward. Now, one thing that we're sort of taking for granted here is the fact that we're rotating about a fixed axis, right? So if we imagine some rigid body that's rotating about, say, the z-axis, well, the angular momentum is going to be parallel to the angular velocity, which means that the angular momentum in the x direction is going to be 0, angular momentum in the y direction is going to be 0, the angular momentum in the z direction is just going to be the moment of inertia times the angular velocity. And from this we can sort of start to construct an expression for the kinetic energy by saying that the kinetic energy is still 1/2 mv squared. We're adding up all of these masses, which in turn follows that this is just going to be 1/2 I omega squared, right? And then we can take a look at this and see how else we can write that. Well, let's think about this. If L is in the direction of omega, then that means that if we were to do, say, L vector dot omega vector, we're just going to get these terms multiplied together, right? Because these are the only terms that are surviving. So that tells us that L dot omega is just going to be this times omega, right? So this is going to be I omega squared. In other words, we can say that K is equal to 1/2 L dot omega. And we can implement our little bracket notation that we started using in the last video, which tells us that this is equal to 1/2 L omega. And we can write this as a bra because, I mean, angular momentum is going to not have any imaginary components here. So it's Hermitian conjugate, it's just still going to be equal to itself, minus the fact that it's now a row vector. And L is just I omega, right? So L vector is equal to I omega vector, and that means that this is equal to 1/2 I, the inner product between omega. Now, if we get rid of that assumption that our object is only able to rotate about a fixed axis, like say we're allowing for the chance that it instantaneously rotates about some point, and we say take that point to be the center of mass, well then the velocity vector now becomes v is equal to omega cross r, right? Because we're allowing it to rotate about some point now. And if we look at the original definition of the angular momentum, remember that L is just equal to r cross v dm. Well, now what's our v? Well, now we have that this is equal to the integral of r cross omega cross r. And we can expand this by using certain cross product identities. I do want to be a bit clear on this notation here. What I'm saying is that r is going to be the distance from that dm to this new instantaneous, this little point that it's rotating about. The cross product identity that we're going to need to simplify this a bit is if we have a vector A cross B cross C, that this is equal to A dot C B minus, these are still vectors, we've got A dot B C. Now, applying this identity to this equation here, what that tells us is that L can then be written as the integral of, we're going to have an R dot R times omega, so we're looking at this one, minus an R times R dot omega dm. Okay? And then we're going to do something that looks a little bit weird at first. What we're going to do is we're going to define the components of this angular momentum. And to do that, we need to talk about the component of W, or of omega, sorry. So we can say that omega, the ith component of omega, is going to equal a sum over j of the jth component times this Kronecker delta, ij. Right? And this might look weird at first, but really that's just an identity, right? It's saying if j doesn't equal I, then this is 0. So it's really just saying that I equals this, or the wi equals this. So we can substitute this in, okay, and we get that the ith component of the angular momentum is equal to the integral, well, r dot r, this now just becomes a, well, let's keep it as r dot r actually. We have r dot r. The ith component of this, so that's going to be the sum over j, omega j delta ij, minus Well, we're looking at the ith component of this position vector, so we're going to write this as xi. Okay, so that's corresponding to this little term here. And then now we need r dot omega. So that's this term that we're about to write here. Let's go ahead and figure out what this is real quick. So I'm going to write this directly under. So r dot omega, or more specifically, so r dot omega is going to equal, well, it's the sum of the components multiplied together, right? So it's the sum of xi omega I, and we're summing over I, so this is just the definition of a dot product. And then what is the definition that we defined up here of omega I? Well, this is equal to the sum over I of xi sum of omega j delta ij. Let's pull out this sum, so we're summing over j here. This is equal to sum over I sum over j xi omega j delta ij. Well, that tells us that this x sub I has to be now the same thing as the j term. So this x sub I is going to become a j, and we can get rid of the sum over I, telling us that this is going to equal, we have xj. Let's add our sum, actually. Let's be explicit. So this is times the sum of xj now times omega j. Okay? And there's no need to write the delta anymore because we really just changed our basis. So here's that times dm. And then we can factor out this sum over omega j outside. We can write this. I'm going to write this, I guess, right here. So that's right here. So we have Li is equal to a sum over j, omega j, times the integral of r dot r delta ij minus xi xj. dm. Okay, so now we've defined our ith component of the angular momentum. And we defined the ijth component of the inertia tensor to just be the stuff that's inside that integral. So we define ij equal to, let's see here, we've got our integral of r dot r inside a bracket minus xi xj dm. So these are the components. This is the component of the inertia tensor. And then this just means that we can write the angular momentum as L, the ith component of the angular momentum, is equal to a sum over j times the jth component of the angular velocity times the inertia tensor, or times the ijth component of the inertia tensor. Okay, and throughout the rest of this series, we're going to be having a lot of these implicit summations. You'll notice that whenever we have two indices that are repeated, we always end up summing over them. So we're going to adopt what's known as the Einstein summation convention, which says that whenever you see two indices, you're summing over them. If I don't do that, then I will explicitly say, by the way, we're not summing over this, even though I've repeated indices. Which means that we can, from now on, start writing things like this as, say, Li is equal to omega j ij. It's assumed that since j is repeated, that we're going to be summing over j. So these were the electric susceptibility tensor and the inertia tensor. Now this is where I really need those of you who watch these videos to provide some input, because for the next video I was planning on moving on to how do two-index tensors transform and things like eigenvalue, eigenvectors, stuff like that. But initially I wanted to cover 4 two-index tensors, which I didn't have time to do in this video. I didn't think it would take this long to just cover 2 of them. So on top of these 2 that I did go over, I wanted to talk about the electric quadrupole tensor, as well as the electromagnetic stress tensor. And I really wanted to do the electromagnetic stress tensor because I thought it was really cool. So this is where I need your input to let me know, should I still make a video on those 2? Should I still make a video on at least the electromagnetic stress tensor? What do you want to see? Are you ready for me to move on? Do you get the picture for the 2-index stuff and why we sort of need them or how to motivate them? If I do, say, make the video on deriving the electromagnetic stress tensor, it would not be pushing back the date of the next one, of the one where I start talking about how these things transform. It would be in addition to. So I just don't know if that's too much for a week or if it's just overkill. Do you guys care to see those? So let me know in the comments section if you want to see this stuff, and I'll see you guys there.